It does show very interesting properties. I hope I will convince you. Uh, uh, so let me just start the story. And this is done by two of my very bright students. A lot of it is simulations, and a lot of it is also some theoretical inputs. So thermalization, right? That should eventually thermalize, or it should become equilibrium. That's what is assumed, and I will show you that it's not necessary. It depends on the various, some initial condition and dimensionality. I don't, well, quantum I will not get into, but I'm just going to discuss with Gross-Piatowski, which is semi-classical. But quantum systems too, we believe, except like time crystal, it is supposed to thermalize. But I'm not going to discuss that part in this talk. So this equation, I'm not sure all of you know about it, but this is a GP equation. Psi is a macroscopic wave function for superfluid or Bose-Einstein condensate superconductivity. Everybody is familiar with all the terms except this term, right? This is a nonlinear term coming from self interaction, okay, and this term makes a lot of difference. It does create new features which I will discuss now. So as I said, I want to discuss isolated system, so I will turn off this potential. No potential is an isolated system on its own. This equation we can rewrite. It has been done before. I am not citing people's work, but this is all done before. So we can write psi as a standard square root n, which is density field, and s is a phase. So this is standard stuff. But if you take the gradient of s, we get macroscopic velocity. This is the velocity of the superfluid, which is measured in the lab. So this is really what we know in experiments. Now we can derive equation for u and n from this equation. So by the way, psi is not an operator, okay? Psi is just a field of position and time. It's a semi-classical, as I said. Now I hope you can see from the back. So the n, which is the density field, which is continuity equation for the mass, right? This is, in fact, if you know fluid mechanics, this is mass conservation, okay? And the second equation is for the velocity field of the superfluid. This is very similar to Navier-Stokes equation, okay? So this is what I work on mostly. So Navier-Stokes equation, u the velocity field, rho is the density. Density is number density multiplied by mass of the quasi particle. Here there are two pressure. This pressure, if you derive it, this pressure comes from this part, the kinetic energy part, and this looks pretty strange, but it is derivable from here. We get this pressure, and this is coming from the nonlinear term Gn squared. Gn squared is, well, is some kind of polytropic gas. We can make connection, and this term is a new term, which is not. It doesn't have a linear classical analog. Okay, so this is quantum part. Now I'm just going to go to the next slide. Quantum systems like GP does not show shocks. So let's go to the next slide, okay. So please remember there are two pressures. One is standard polytropic pressure equivalent, but it's n squared, not like 4/3 or 5/3 of normal gas, but it is polytropic gas. But this is the new quantum pressure. Now I am going to relate this to Euler equation, okay. This is one of the classic equation nonlinear of nonlinear fluid, nonlinear field theory. So this is basically the same equation with viscosity 0, and this pressure is polytropic pressure, okay. So P, we can assume, well, various kinds of pressure. For photons we have some P, but just P is a pressure, okay, thermodynamic pressure, and these are same equation, continuity equation, okay. Now this equation remains still unsolved. I will not get into what are the unsolved problems, like does it have solution, what kind of solution, does it have singularity, but will not get into the math part of this. So this is a compressible Euler, it's called, because the density field is changing. Now a lot of people work in incompressible Euler, which I will not discuss in this talk, but this is also a very important equation where density is constant, okay. But we focus on this equation because it's similar to GP. Like GP equation, I am just going to put it below, here. So this equation, they look very similar except the new term, the quantum pressure term, okay. So we are going to discuss both these equations. There are some similarities, there are some dissimilarities. One major dissimilarity is that Euler equation gives shocks. Now shocks are very easy to understand. If you have a road and some cars are moving fast and some cars moving slow, so they will be piled up, right? This road traffic jam, that is shock. That happens in fast fluid going behind the slow fluid. Okay, shocks are here because the fluid, I mean there is a density variation, shocks are property of this, but this GP does not give shocks. Okay, because this term, well, I will not get into the math part, we get basically vortices, superfluid vortices, vortex empty, vortex no shocks, okay, and that leads to different kind of behavior. Now one equation I am going to discuss along with this is called Berger's equation, which is a very special case where pressure is 0. So if it is very compressible fluid like mud, so it has no repelling pressure, so it has the pressure 0 and it leads to real shocks. Okay, I am just going to start with Berger's equation. This is very well studied, we know exact solution for Berger's equation. So we will start with Berger's and let us see what we get. Okay, but before I go there, I am just going to discuss this equilibrium solution. Okay. So we just go slow. Some of it people know about it, but I am just repeating it. So this in fact one of the first papers is by T.D. Lee, the Nobel laureate in high energy physics. So he had the solution in Krecknen. So let me just give you a simple solution. There are some complications, but I am just going to strip off the complicated part, just the simple solution. So is random, no? So in fact random uncorrelated. So we will see some random stuff which is correlated, but random uncorrelated is a velocity field correlation will be delta function, and if I do the Fourier transform I will get equipartition of energy. All Fourier modes will have same energy. That is a key part of this thermalized part. So in fact thermalization I mean this, equipartition among all Fourier modes, not particles, we do not have particles, the fields, all the Fourier modes are equal energy, and as a consequence if you look at the shell energy, or we call density of state in condensed matter physics, so 1D it will be constant, this is basically 1D, but in 2 dimension I need to sum over a shell, it becomes k, and 3D is k squared. Okay. Now if I see this stuff, can I say that my system is thermalized? I need something more, I want to do detailed balance. Okay. So what is meant by detailed balance? I do not want any energy exchange among Fourier modes. I want to say, well, this Fourier mode is not losing any energy to other Fourier modes in general on the average, and that comes from very nice property which I am trying to push, that this is one way to see thermalization. Okay, I want to impress upon condensed matter physics that you can use this definition for thermalization or non-thermalization. Okay, so let us go slow. So this is a UK is a Fourier mode. So this called energy mode. Okay, I mean this is there in all fields, condensed matter as well. Now if I look at the equation for the energy, so this is my equation, I am abstracting it. So this is the d by dt of UK, linear term, like Laplacian will be linear term, and this is the term which is non-linear term. You multiply by the complex conjugate of UK and add the complex, well from here I can derive energy for equation for this energy. Okay, and that is like this. It turns out the linear term typically goes away. If I take the real part of this, linear part goes away. This Tk, the nonlinear transfer from the nonlinear term. Okay, so if you have pure wave, there is no energy exchange among Fourier modes, that is standard, but nonlinear term does give energy, and we should check whether Tk is non-zero or 0. That is a great measure, and that is what I am going to tell you, that it gives you a good signal for thermalization or equipartition, equilibrium or not. Now we define in hydrodynamics, this cosmograph flux is a key ingredient. So we can define flux. So I can do the integral over a wave number sphere, which is here. So I have wave number sphere here, and I take a sphere of radius k, and if we integrate this, so integral of Tk is called flux, this cosmograph flux. The standard analogy is if a coffee cup, I stir coffee, then I am supplying energy at large scale and energy cascade to small scale, and this is a flux in Fourier space, is energy going from small wave numbers to large wave numbers. Okay. Now we want to see whether this flux is 0 or non-zero. So flux is 0, that means kind of thermalized. Okay, flux non-zero is non-thermal, and that is what I will test. So Tk 0 is equilibrium, Tk non-zero is non-equilibrium. Okay, so that is standard stuff I am going to use for my solutions. Now with this background, let's look at 1D system. We start with Burger's. Burger's equation, if I start with random noise, so velocity field you can start with random, then it remains random. This is a random noise, and here Ek is, it's random noise, it's a white noise, equilibrium, no Tk, 0. But if I start with sin x initial condition, like sine wave, like some cars are moving fast, some cars are moving slow. Yeah.
So you do not care about the distribution of energies in various K modes. As long as they're not exchanging it, you are saying it's equilibrium.
No. Yes, as long as there no exchange.
But in general, isn't that a steady state rather than equilibrium? Because equilibrium should refer to some sort of a distribution, like a Boltzmann.
Next slide, I am going to show an example. Exactly, hopefully they will answer your question. Give me 1 minute, okay. So this is a sine starting initial condition, we get shocks, and for this, this is non-equilibrium, okay. So this is coming from this solution, it is non-equilibrium, but if you wait for long enough time, there will be some thermal noise, some noise which will lead to perturbation and it reached there. That's assumed, I think it will happen. In fact, their work by Frisch or Samriddhi in ICT. So these people work on this kind of stuff. Now to answer your question, let's look at GP. That's my main topic. So this is gross speed equation in 1D, solitons, right? So 1D single soliton, this is solution, okay, standard. Now I am going to ask you, is it equilibrium or non-equilibrium? Is it thermalized or non-thermalized? If you look at the spectrum, it is not not constant. Now how do I measure it? By the way, soliton just moves, it does not do anything, stable structure. So look at for Tk, the Tk, and Tk is 0, 10 power minus 10, 11, 10 power minus 11. Tk is 0 for this, so that means it is an equilibrium solution, though it is not white noise. So I think this, so we will see structures which are not interacting among themselves, but the structure is sitting there like peace, you know. So this is a one solution which is not white noise, but it is equilibrium according to me, okay. So that's what we believe. Now if you look at two solitons, what happens to two solitons? Far away they are at peace, but they come close, Tk becomes non-zero. In fact, Tk becomes pretty large, and I'm just going to play a movie here. Come on, yeah. So here you see the Tk, when they come close, this energy exchange among Fourier modes is huge, and that is non-equilibrium. So two solitons is non-equilibrium, single soliton is equilibrium by this definition. Now let's look at well, by the way, so there is very beautiful paper Ansager. So structures can come in equilibrium physics. So this paper shows that we can have like Ising spin, no? So there is a negative temperature state which can lead to negative, well, it can lead to structures in equilibrium systems, but the way I am going is from non-equilibrium perspective Tk. So I am not going to discuss this, but this is one aspect we will use. Now let us look at 3D. So we do again simulate with initial condition. Now this is a tricky part, but believe me that we start with called Taylor-Green vortex and random initial condition. So these are two initial conditions we choose, and we can do Euler, compressible Euler, as well as Grotz-Pityvsky. So quantum is GP, and this is left one is Euler. So what happens here, you can see that these two guys, quantum is basically random. I am going to show you by spectrum. Quantum is thermalizing, but classical is not. So how do I see it? Let us look at the spectrum. So these are, okay, now I want to tell a little bit. So this velocity field has two parts called compressible part and rotational part, incompressible part, and the so look, so I am going to analyze these two, okay. So in quantum system, these two, the spectrum is k squared, in 3D thermalized, okay. And if you look at Tk, Tk is pretty tiny, this is Tk, it is nearly 0. But if you look at classical systems, this is not k squared. In fact, there are structures here which are not really thermalized, okay. So classical Euler system, in fact these are very long runs, around 200 degree turnover times. These systems are not thermalized in Euler, is going on and on, and so this is also important part. Tk we do running average. I do running average of quantum systems is basically 0, this is the flux. But if I look at compressible Euler, then running average is basically not setting it to 0. So there is an energy flux which is non-zero, and quantum systems are not, the Euler is not thermalizing in 3D. So I mean this is another movie, but I think I'm just going to. So in fact, there is a energy transfer from incompressible to compressible. That is a key part for this stuff. So there's one more slide. So this is a very nice simulation which we did with colleagues in IIT Jammu. So normally we do Boltzmann equation. We start with random initial condition. So this is a MD set solution. So we start with rotation. So we don't start with random initial condition. Okay. I was asking a lot of MD simulation guys, but nobody was really thinking about this. But start with vortex. So we have atmosphere out there, and atmosphere is basically they are large vortex, right? I mean all the time. The hurricanes are prime examples, but we have hurricanes, small hurricanes all the time. So we start with this velocity field, which is initial condition is vortex, but with a white noise, thermal noise embedded on it. Let go, then this is 2000 called Leonard-Jones time, okay. So this is LJ times, LJ units. If you think of eddy turnover time is what one unit of time it will go around, make one rotation. If you wait for long enough time, this MD simulation does thermalize, okay. So we get K minus 3 spectrum here. This is coming from structure, we can show it that this is follows from the structure K minus 3, but this is K. This is interesting, right. So at small scale there is thermalization, but not at large scales. So in fact this is what we should look at atmosphere. Atmosphere large scale is in fact structures which is not thermal, but small scale is thermal. People do not pay attention to this. I think this comes from fluid mechanics. System can be both equilibrium and non-equilibrium. So this part is equilibrium, but this part is non-equilibrium. But wait for long enough time is basically the structure is destroyed and we get there. It may happen like in Burger's equation, structure will go away and thermalize finally. But I am not sure. 2D, the Euler in 3 dimension is just going on and on. Structures may persist for long time. So we do not know, but we ran it for long time in 3D. Whether this will disappear at 10,000 time, we can't say. But now this is for 3D. Now let us go to one more point. In isolated systems, by the way, this some of it is not new. I mean, this is like people talk about it, but I do want to tell you in condensed matter physics community what we know in fluid mechanics. Does isolated system have viscosity, or can it have friction? Now this is an example where we have a vortex, but it disappears. Well, this vortex structure disappears and it becomes noisy. So what's happening here? Here this is we have a coherent structure. So I divide this velocity field into hydro part and fluctuating part. I split in 2 parts, and then we do the energy for this. So energy will be coming from this one and this one. The cross term is 0. So in this part what's happening is we have more of this part and less of this part, but if we wait for long enough time everything becomes noisy. So the conversion from structured to unstructured noise, and that is friction. In fact, what is viscosity? Viscosity is essentially modeling this one is a dissipation. So isolated systems can have viscosity, effective viscosity, that is what we put in fluid mechanics. Now I am going to go to 2D systems, which is 2D has always been tricky, but now I am just going to show some examples. So we start again with TGV, Taylor-Green vortex, and shear. So this is the initial condition, okay, and we will do both the simulations. GP, quantum is GP, and classical is classical Euler. Okay. Now here this one shear thermalizes. I will show you that this will thermalize, but TGV does not thermalize. TG is thermalized in some sense, but TGV is showing you solid structure which is sitting here. Okay. Now let us look at, but classically they are again structures, and let us look at quickly look at them. quantum is showing, this one is showing a k, that means this is thermalized, but this one is showing k minus 3, this one, and compressor part is showing k. So k minus 3 does not look like thermalized, no, this provided structure, but if I look at Tk, Tk shows 0, Tk is basically 0. If you look at quantum shear, a quantum TGV, average Tk, average flux is 0. But those classical structures, the Tk and the flux is non-zero, and these are basically stay put for long time, and so I hope you are convinced that classical 2D, the structures are there and it is non-thermal, and you wait for long enough time, you have done some other stuff like incompressible Euler, it does not thermalize, it is isolated by the way. So let us play this movie then. So here the Tk is basically significant, this for 2D Euler. Here there are, okay, I do not want to bore you with this, but there are 3 fluxes corresponding to the different velocity components. Now 2D quantum, this structure which is solid structure, it does not change, the structure stays put, and we get basically if I average out running average, I get Tk. So this is a pretty much in 2D the quantum part, those there is a structure, so this is surprise part, okay. We do not need a white noise to thermalize, and this is showing thermalized stuff. Yeah. No, this is Gp is a classical equation describing a superfluid. So my the psi is not an operator, so there is no commutation relation in this. Psi is a classical field, okay. Sorry, it is a superfluid, the superfluid quantity. Okay, now I think I am just going to close my discussion, talk. Okay, now I just want to say this. So if I look at the evolution of the system, like especially 2D incompressible, we did study in great detail, system does become ordered, more ordered with time. Okay, you may get surprised, but 2D Euler it does get more ordered. In fact, you see that I start with random initial condition, pretty well, not exactly random, but start with it just get more ordered. Now I did not put the slide here, but for Euler equation, since there is no viscosity, entropy is 0, entropy is constant, there is no entropy production. If the thermodynamic entropy is constant, how do I quantify order or structures? Okay, I mean you may use the word order. How do I quantify order in a system where thermodynamic entropy is constant? So we devised, in fact it is also known in other communities like electrical engineering. So we can define in terms of power spectrum. This is what I will end with. So we given a field we can define, I can get Ek, which is Fourier modal energy. Modal energy we divide by time, we call it Pk, probability for Wave number k. Sum of Pk is 1 by definition. So I can define entropy called minus Pk log Pk, borrowing from Shannon, but it is not quite Shannon, okay. This is in Fourier space, and this entropy shows very interesting properties. Like for 2D system, this entropy will decrease with time. Okay. Now I am not violating second law of thermodynamics, I am not reading work out of anywhere, but this is a new measure for order. In fact, there is a contradiction, there is a problem if you just stick to thermodynamic entropy. So I think with this I will close my talk. So 1D there is a shock which becomes random Euler. Gp is a soliton, it is not random, but still I will call it equilibrium. I hope that answers your question. In 2D, 3D is kind of trivial. Gp thermalizes, Euler is like shocks but may thermalize for long enough time, but 2D is a lot of surprise. 2D Euler is definitely non-equilibrium, and Gp is one solution is random, other solution is structure, but both of them are Tk is 0, Tk is nearly 0. So I think I will end here. Thank you.
Thanks, Professor Verma, for a very nice talk. We have time for a few questions.
Yes, he's asking. Okay, no, she is.
So since your system is closed, so the energy has to be either distributed or it can oscillate between
Yes.
modes. So in your case, it oscillates between these various scales. Is that possible?
So oscillate means it's not a periodic oscillation. So
I understand.
the example is, okay, there's analogy. Okay, so
It goes from one
no,
scale
no.
to
Let me make an
another.
analogy, which is, so there are many modes. So normally the high wave number modes are thermalized, like we saw for MD simulation. But the low wave number modes, like analogy, large companies, they're huge dynamics among themselves, but the poor people or normal middle class is basically thermalized. So there are huge number of modes which are interacting among themselves, exchanging a lot of energy, which is non-equilibrium, especially in 2D, and they just keep exchanging. It's not some kind of ordered energy going back and forth, not going over structures, but they are exchanging among themselves, playing their game. That's the best I can think of, and it does show like that. Yeah.
Another question is, there are many questions. So another question is, why are these structures so stable? Is it because some kind of topological defect kind of stuff, like vortices and anti-vortices separated along they can take a long time.
Okay, I don't know topology, so I should be, but I think it is. In fact, uh, the interactions are such a way that, well, for example, I don't know, I can't say, but it is comes out of uh, uh, such. I think the non interactions are leading to that.
So okay, we can have one last question because we are running late.
So in case of your 1D system, you had like solitons. So
Right.
how did you produce the solitons? Is it because your interaction is attractive or yeah, like
So, Gross-Petit equation does give soliton. It is, in fact, you can map it to potential well, and there is a, so GP does show solitons like KdV equation. KdV equation does, so at least when there is a nonlinearity, will try to steepen it, and there is a diffusion, not dissipation. So diffusion and nonlinearity oppose each other, and the structure is a stable solution.
Dispersion, non-linearity concept dispersion.
like you have at some point you have suggested
I
that one
think
should take
we can
contact
postpone this question for discussion because.
Okay.
Okay, that's the last question. I already said last.
What is the source of nonlinearity here?
So part interaction, self interaction of the bosons, that's a linearity. So there are boson in condensate, no, there are many of them. So that is what is self interaction. Okay, thank you.
So in the interest of time, we'll move on to the next talk.